All right, here we go. Unit 7, Lesson 1, the final unit. This unit is called Advanced Applications of Integration. So we're there. We're all the way to the finish line. And it turns out that there is a second fundamental theorem of calculus, or rather there is a part 2 to the first part, but I like to just refer to it as the second fundamental theorem of calculus. Don't worry, it's way easier than the first one. Especially to prove. It'll take 2 seconds to prove if you grant me that the first one is real. So let's talk about the first one, right? This is something you want to, if you're going to get a tattoo, this is what you should get it of. This is the first fundamental theorem of calculus. Remember, it says that the definite integral of some function, which represents the area between that function and the x-axis, can be found by taking the antiderivative, right? Taking the antiderivative, plugging in the top limit of integration, plugging in the bottom limit, and subtracting them. So it's really important because it links area under the curve and the derivative, right? So it's a very important concept. But what I want you to imagine, and here's the second fundamental theorem of calculus. Let's imagine a function, I'm going to call it g of x, where normally a and b, right, these are constants, right? These are constant numbers, like from 2 to 4. Well, what happens when I change this, at least one of them, to a variable? And so the way you want to picture this, right, is like imagine you have this function g of x, and I'm kind of rolling my paintbrush along, and what x tells me is how far to roll my paintbrush. And it's a function where x goes in and g of x computes the area under the curve up until that point. So that's what this is saying here, is like start at a and go to whatever x is. But then we plot all of those areas on some other function. So like if this was f of t, as we go to the right, as x increases, I'll do like a quick silly sketch, g would only be going up, right? G would only be going up because as long as you are moving x farther to the right, you're getting more area. All right, so that's what these functions are describing. And what the second fundamental theorem of calculus helps us do is take derivatives of functions that are defined as integrals. And so what would the derivative of this be? What would g prime be? And so let's think here, okay, derivative with respect to x, I'm assuming, of g of x. I do the same thing to both sides. And so the question we're asking ourselves here is what would the derivative of this integral be that is partially defined by a variable? Well, on this side, we've got g prime of x. On the right side, I have really no idea what to do here, but I do know I can apply the first fundamental theorem. This is capital F, the antiderivative, plug in x, minus capital F, plug in a. And now here is the super fun trick. What is the derivative of the antiderivative of f of x? Well, that one's easy. The derivative of the antiderivative, now we're back to f. But notice all that happened was I took that t and I replaced it with x. I plug in x. But it's the same thing here, right? Just taking the derivative of the antiderivative brings us back to our starting point. Now here is the part that if you get this next like 30 seconds here, the whole thing will make sense. What is the derivative of the antiderivative of f at a? And here is the magic. It's 0. It's 0 because x is a variable, so we take that derivative and we get lowercase f. But f of a is just a number, right? It's like, because a could be 3 or 2. A is not a variable. It is a stand-in for some number. So it is a stand-in for, like, we define g of x to be from 2 to x. And so it's not a variable. It's like, oh, I plugged in 2 and I got 7. Take the derivative, gone. So this is really interesting here. The derivative of a definite integral, it looks like you just kind of get rid of the definite integral, right? And for the most part, that is actually literally just what happens. It's like you can get rid of, they undo each other. Now, it's almost exactly how it works. And it does work well in this case, but it's the special case of when this is just an x. You might be suspicious here, and yes, the chain rule is going to be involved. So let's say we did g prime of x of this thing here. Well, we'd have the derivative of, and I'm going to save a little bit of paper here. I'm just going to skip straight to the fundamental theorem part 1. This is f of x squared minus capital F of a. And so what we have here, well, the derivative of capital F of x squared is lowercase f of x squared chain rule times 2x. The derivative of capital F of a, this is still just a constant number. This is a number. This is not a variable. And so what we have here is f of x squared times 2x. And so I'm going to tell you the short and sweet version right now. Here's the second fundamental theorem of calculus. Take your top limit, plug it in for whatever variable is in your integrand, and then don't forget the chain rule. That's essentially all that is happening here. That is the second fundamental theorem of calculus. So the second fundamental theorem of calculus says, if you have, and I missed it, I wrote it down here, so let's talk about it here. If you have h of x is some function from the definite integral from a to g of x of f of t, what we're going to have here is literally just take exactly this integrand, don't do anything to it, stick your g of x in there, chain rule times g prime of x. And so this is, I like to state it this way, if you look up this theorem, you're going to see this. And to me, just be careful. This hides that there's a sneaky times 1 here from the chain rule. And so if I say the second fundamental theorem, I'll often present it this way. But just remember, there's chain rule going on here. And so we're just going to do like 2 quick examples here. And that is actually going to be it. So here we go. If we have f of x, capital F of x is the definite integral from 1 to x of 4t minus t squared, and I want to find the derivative of this function. What the second fundamental theorem tells us is that I can literally just plug in x here. This is 4x minus x squared. And you're saying, are you kidding me, Mr. Bird? That's it? Yes, that's literally it. But the only thing that will make this slightly different is if this is an x squared here, but it's really, this is literally it. If I take this derivative, the derivative here would be 6 times the square root of x squared times 2x. So I plugged that x squared in for t, and I did the chain rule on x squared. So we're going to have 6x times 2x. Yes, this is literally just 12x squared. So that's the second fundamental theorem. Actually, I put in 2 exact ones from Delta Math 2, or, I think we're just going to do this one. I'm not even going to assign that bottom type because I want you to spend plenty of time on the summative today. If we find the expression for f prime of x, okay, so I see this is not just x, so the alarm bells go off here. Don't forget the chain rule. Don't forget the chain rule, but I am just going to plug this sucker in here. The cosine of 2 root x times, okay, well, this is x to the 1/2. Okay, so the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And I could play around here. I could try and turn this into the cosine of 2 times the square root of x all over 2 times the square root of x, right? When you take this negative 1/2 and you move it down. Or, again, feel free. It's totally reasonable to just leave this as times 1/2 x to the negative 1/2. And that's it for the first half. That's it for part A, the fundamental theorem of calculus, part 2. And so I'm just going to finish this off here. If you have h of x is the derivative, or is the definite integral from a to some function g, which may just be an x, of f of t with respect to t, h prime of x, this is a memorized one. You take the derivative of this, it's literally take your integrand, plug in this top one here, times g prime of x. And we can prove that, and we did prove it using the first fundamental theorem, but it's a good thing to just kind of commit to memory.